Have you ever dreamed of becoming invisible? To slip unseen through the world, a silent observer of reality? For centuries this idea belonged to myth and fantasy. It was the stuff of magic wands and fairy tales. But what if I told you that we are standing on the threshold of making it real? Not with magic, but with science. A new kind of material, unlike anything found in nature, holds the key. These are not materials we dig from the ground or grow in a field. They are materials we design, molecule by molecule, to perform extraordinary feats. They challenge our very understanding of how the universe works. This journey into the impossible begins with a simple question: how do we see things? We see objects because light bounces off them and travels to our eyes. Your brain then processes these signals into an image. So, to make something invisible, you would need to guide light around it, as if it were never there. Imagine a river flowing around a smooth stone. The water parts, flows past the stone and rejoins on the other side, leaving the water downstream undisturbed. What if we could do the same with light? This is the promise of a revolutionary field of science, one that asks us to rethink the very nature of matter itself. The materials that could achieve this are called metamaterials. The name itself gives us a clue. The prefix meta comes from Greek, meaning beyond. These are materials that go beyond the ordinary. They possess properties not found in the elements of the periodic table or the compounds they naturally form. They are born from human ingenuity, carefully crafted structures designed to interact with light and other forms of energy in ways we once thought were forbidden by the laws of physics. They are a testament to our relentless curiosity, our desire to not just observe the cosmos, but to become active participants in its grand design. So let us embark on a journey of discovery. Let's explore this strange new landscape of matter. We will travel from the realm of imagination to the cutting edge of laboratory research. We will see how human creativity is unlocking the hidden potential of the universe. Forget what you think you know about how materials are supposed to behave. The universe is far more clever and surprising than we ever imagined, and we are just beginning to learn its secrets. Prepare to have your mind expanded. The future is being built, one tiny, engineered structure at a time. So what exactly is a metamaterial? Let's break it down. Think about a block of gold. Its properties, its color, its density, its conductivity, come from the gold atoms themselves. The same is true for water, wood, or plastic. The properties of these materials are determined by their chemical composition. They are a gift from nature. Metamaterials, however, are different. Their amazing abilities don't come from what they're made of. They come from how they are built. Their power lies in their structure, their architecture, on a scale smaller than the wavelength of light itself. Imagine building with Lego bricks. You can use the same red, blue, and yellow bricks to build a simple house or a complex spaceship. The properties of the final creation depend not on the plastic bricks themselves but on how you arrange them. Metamaterials are like that, but on a microscopic scale. Scientists use ordinary materials like tiny bits of metal and plastic. They arrange them into intricate, repeating patterns. These patterns are so small and precise that they can interact with electromagnetic waves, like light, microwaves, or radio waves, in very specific and unnatural ways. It is the pattern that does the work. This is a profound shift in our thinking. For all of human history, we were limited by the materials we could find. We searched for the strongest wood, the purest metal, the clearest crystal. We were material finders. Now, we are becoming material designers. We are no longer bound by the inherent properties of atoms and molecules alone. We can create materials with properties that are, quite literally, off the charts. We can design a material that bends light backward, something no natural substance can do. We are writing new rules for how matter and energy can interact. The key idea to remember is this: structure, not substance. A metamaterial's magic isn't in its chemistry, it is in its geometry. This is why they are called metamaterials. They are a step beyond. By controlling the shape, size, and spacing of these tiny engineered structures, we can control how they respond to energy passing through them. We can make them absorb sound perfectly, focus light to a point smaller than we thought possible, or yes, even guide light around an object. It's a whole new toolbox for inventors and engineers, and it's opening up a universe of possibilities. How do you build something whose features are smaller than a wavelength of light? The process of creating metamaterials is a marvel of modern engineering. It requires precision on a scale that is difficult to comprehend. We are talking about nanometers, billionths of a meter. To put that in perspective, a single sheet of paper is about 100,000 nanometers thick. The structures that make up a metamaterial are thousands of times smaller. This is not carpentry or metalworking. This is sculpting with atoms, a field known as nanotechnology. It is where science and engineering meet at the smallest possible scales. Scientists use techniques borrowed from the computer chip industry. One common method is called photolithography. Think of it as a highly advanced form of photography. Researchers start with a flat wafer, often made of silicon. They coat it with a light-sensitive material. Then they shine ultraviolet light through a mask, which acts like a stencil, projecting the desired intricate pattern onto the wafer. The light alters the coating, and a chemical process washes away the exposed or unexposed parts, leaving behind the microscopic structure. This process is repeated layer by layer, building up a complex three-dimensional architecture. Another powerful technique is electron beam lithography. Instead of using light, this method uses a focused beam of electrons to draw the pattern directly onto the surface. It is like writing with an incredibly fine pen, allowing for even smaller and more precise structures. Other methods involve self-assembly, where tiny components are designed to automatically arrange themselves into the desired pattern, like microscopic crystals growing into a pre-programmed shape. Each of these methods allows us to build materials from the ground up, giving us unprecedented control over their fundamental properties. This is what makes metamaterials so profoundly different from normal materials. A diamond is hard because of the strong chemical bonds between its carbon atoms. Water is wet because of the way its H2O molecules interact. These properties are intrinsic, but a metamaterial's properties are extrinsic. They are engineered. By changing the pattern, we can change the property. We can tune a material to interact with a specific frequency of light, from visible light to radio waves. This level of control is simply not possible with natural materials. We have moved beyond merely discovering what nature has to offer, and have begun to dictate our own terms. Now let's get back to that invisibility cloak. How does a metamaterial actually make something disappear? The secret lies in a property called the index of refraction. This is a measure of how much a material bends light. When light passes from air into water, it bends. That's why a straw in a glass of water looks broken at the surface. Every natural material, water, glass, diamond, has a positive refractive index. This means they always bend light in a predictable forward direction. But what if a material could have a negative refractive index? This is where metamaterials perform their most famous trick. By arranging their tiny structures in just the right way, scientists can create a material that bends light backward. This is something that was once thought to be physically impossible. When light hits a metamaterial with a negative refractive index, it doesn't behave normally. Instead of reflecting off or passing through in a straight line, it can be guided along a carefully designed path. It's like having a traffic controller for light itself, telling each light wave exactly where to go. This exotic property is the engine that drives the concept of an invisibility cloak. Imagine an object you want to hide. You surround it with a shell made of this special metamaterial. When light waves from a flashlight or the sun approach the object, the metamaterial cloak goes to work. It doesn't absorb the light, and it doesn't reflect it. Instead, it steers the light waves smoothly around the object, just like that river flowing around the stone. The light waves are guided along the cloak's surface, rejoin on the other side, and continue on their original path as if nothing was ever in their way. For an observer on the other side, the light reaches their eyes completely undisturbed. The object inside the cloak is hidden from view, because no light has bounced off it. It casts no shadow, and creates no reflection. It is, for all intents and purposes, invisible. While a perfect broadband invisibility cloak that works for all colors of light is still a huge challenge, scientists have already built working prototypes. These early cloaks can hide small objects from specific frequencies of light, like microwaves or a particular color of red or green. It's a proof of concept that shows the physics works. We have taken the first concrete steps out of science fiction and into the realm of scientific fact. While invisibility cloaks capture the imagination, the same physics that bends light backward can lead to another revolutionary invention: the superlens. For centuries, the power of our microscopes has been limited by something called the diffraction limit. This is a fundamental rule of optics that says you cannot use light to see details that are smaller than about half the wavelength of that light. It's kind of like trying to paint a tiny dot with a very thick brush. No matter how skilled you are, you just can't create a feature smaller than the brush tip. This limit has prevented us from seeing the finest details of our world, like the inner workings of a living cell or the precise structure of a virus. Metamaterials offer a way to smash through this barrier. A conventional lens made of glass works by capturing the light waves that travel far from an object. But there is another kind of light wave, called an evanescent wave, that contains the really fine, detailed information. These waves fade away almost instantly and never travel far enough to reach a traditional microscope lens. They carry the sub-wavelength details that have always been lost to us. A super lens, made from a metamaterial with a negative refractive index, can capture and refocus these fleeting evanescent waves. By capturing this lost information, a metamaterial superlens can create an image with a resolution far greater than what the diffraction limit allows. It's like trading that thick paintbrush for an impossibly sharp needle. Scientists have already used this technology to see objects on the nanoscale, opening a new window into the microscopic universe. Just imagine being able to watch a virus infect a cell in real time, observing the intricate dance of proteins and DNA. This could totally revolutionize medicine, allowing us to diagnose diseases earlier and design more effective drugs. The implications are, honestly, staggering. In biology, we could unravel the deepest mysteries of life. In materials science, we could inspect the atomic structure of new alloys and semiconductors. In manufacturing, we could ensure the flawless construction of next-generation computer chips. The superlens is not just a better microscope, it's a paradigm shift. It promises to make the invisible visible, not by cloaking, but by revealing the exquisite hidden details of the world all around us. It's a tool that could accelerate discovery in countless fields of science and technology. Our modern world runs on waves we cannot see. Wi-Fi, 5G, satellite communications, they all rely on the transmission of information through the electromagnetic spectrum. The efficiency and speed of these connections depend heavily on the antennas that send and receive these signals. For decades, the design of antennas has been a game of trade-offs. You could have a small antenna that wasn't very powerful, or a powerful antenna that was large and bulky. This is another area where metamaterials are poised to change everything, making our digital world faster, clearer, and more efficient. Metamaterials can be engineered to manipulate radio waves and microwaves with the same precision they apply to light. By incorporating metamaterial structures into an antenna, engineers can make it smaller, more powerful, and more versatile. Imagine a smartphone with an antenna that can find the strongest signal no matter how you hold it, eliminating dropped calls forever. Or think of satellite dishes that are flat, thin, and lightweight, instead of the bulky, curved dishes we use today. These could be easily mounted on cars, airplanes, and even drones, providing high-speed internet access anywhere on the planet. This technology is already making its way into the real world. Companies are developing flat-panel satellite antennas that use metamaterials to steer a beam of radio waves electronically without any moving parts. This makes them more reliable, less expensive, and far more adaptable than their mechanical counterparts. For the next generation of wireless communication like 6G and beyond, we will need to transmit enormous amounts of data at much higher frequencies. Metamaterials are the key to designing the compact, efficient antennas that will make this high-speed future a reality. The impact extends beyond personal devices and internet access. In aerospace and defense, metamaterial antennas can lead to better radar systems that are harder to detect. In astronomy, they could help radio telescopes focus on faint signals from distant galaxies with greater sensitivity. By giving us unprecedented control over the radio frequency spectrum, metamaterials provide a powerful new tool for communication. They will help us build the invisible infrastructure of the 21st century, a global nervous system connecting people, devices, and information in ways we are only just beginning to imagine. The power of metamaterials extends deep into the realm of human health. The same principles that guide light and radio waves can also be applied to other forms of energy used in medicine, such as magnetic fields and ultrasound. This opens up exciting new possibilities for diagnosing and treating diseases with greater precision and less harm to the patient. One of the most promising applications is in magnetic resonance imaging, or MRI. MRI machines use powerful magnets and radio waves to create detailed images of our organs and tissues, but the process can be slow, and the images sometimes lack clarity. Metamaterials can act as a kind of focusing lens for the magnetic fields used in MRI. By placing a specially designed metamaterial pad near the part of the body being scanned, doctors can enhance the signal quality significantly. This allows them to get clearer, higher-resolution images in a fraction of the time. For the patient, this means a shorter, more comfortable experience inside the noisy, confining MRI tube. For doctors, it means a better look at what's happening inside the body, potentially revealing tumors or injuries that might have been missed with a conventional scan. This technology is already being tested and is showing remarkable results. Beyond imaging, metamaterials could revolutionize therapeutic treatments. Ultrasound, which uses high-frequency sound waves, is often used to break up kidney stones or target tumors. However, focusing that sound energy precisely can be difficult, especially when it has to pass through bone, like the skull. A metamaterial acoustic lens could be designed to correct for the distortion caused by the skull, allowing doctors to focus ultrasound beams deep inside the brain with pinpoint accuracy. This could lead to non-invasive treatments for brain tumors, Parkinson's disease or epilepsy, without ever needing to make an incision. The future of medicine is moving toward treatments that are more targeted, less invasive, and personalized for each patient. Metamaterials are a perfect fit for this vision. Imagine smart bandages that use metamaterial sensors to monitor a wound's healing process, or highly targeted drug delivery systems that use focused energy to release medicine at a specific location within the body. By giving us the ability to control and manipulate energy with surgical precision, metamaterials offer a new set of tools for the medical toolkit. They promise a future where we can heal the body with the subtle power of waves, not just the blade of a scalpel. For all their incredible promise, the journey of metamaterials from the laboratory to our daily lives is not without its challenges. The path of scientific progress is rarely a straight line. It is filled with obstacles, setbacks, and moments of brilliant breakthrough. One of the biggest hurdles is manufacturing. Creating these intricate nanometer-scale structures is currently a complex and expensive process. Scaling up production from a single tiny prototype in a lab to millions of devices for the consumer market is a massive engineering challenge. We need to find ways to build them cheaper, faster, and bigger. Another significant challenge lies in bandwidth. Many of the most stunning demonstrations, like the first invisibility cloaks, worked only for a very narrow range of frequencies. A single color of light or a specific microwave frequency. A cloak that only hides you from green light isn't very useful in the real world, which is bathed in the full spectrum of sunlight. Scientists are working hard to design more complex metamaterials that can operate over a broad range of frequencies. This requires multi-layered three-dimensional structures that are even more difficult to design and fabricate, pushing the limits of our computational and manufacturing capabilities. Despite these hurdles, the progress has been breathtaking. What began as a purely theoretical concept just a few decades ago has blossomed into a vibrant and dynamic field of experimental science. We have seen real working prototypes of invisibility cloaks, super lenses that defy the diffraction limit, and flat antennas that can talk to satellites in orbit. Each of these triumphs serves as a crucial stepping stone, proving that the fundamental physics is sound and inspiring a new generation of scientists and engineers to tackle the remaining challenges. The field is advancing rapidly. New design techniques using artificial intelligence are helping us discover novel metamaterial structures with surprising properties. Breakthroughs in 3D printing and self-assembly are making fabrication more accessible and affordable. The journey is far from over, but the momentum is undeniable. Every challenge we overcome brings us one step closer to unlocking the full potential of these extraordinary materials. The story of metamaterials is a powerful reminder that with persistence and imagination, humanity can learn to engineer the world in ways that were once confined to our dreams. We stand at a remarkable moment in history. For millennia, we were explorers of a world made of natural materials. Now we are becoming the architects of a new world, one built from materials of our own design. Metamaterials represent more than just a technological advancement. They represent a fundamental shift in our relationship with the physical universe. They show us that the properties of matter are not fixed, but are malleable, programmable, and limited only by our own creativity. Understanding this is crucial because these materials will shape the technology and the society of the future. The possibilities stretch as far as our imagination can reach. Think of buildings coated in metamaterials that can perfectly absorb the energy of an earthquake, protecting cities from devastation. Imagine windows that can switch from transparent to a perfect mirror, helping to cool our homes without air conditioning. Consider computers that use light instead of electrons to process information, running thousands of times faster and more efficiently than today's machines. These are not fantasies, they are the logical extensions of the science we are developing today. Metamaterials are a foundational technology, a building block upon which countless future innovations will be built. This is why learning about metamaterials matters. It's not just for physicists and engineers in a lab. Understanding this revolution helps us all appreciate the power of scientific inquiry and human ingenuity. It inspires the next generation of thinkers, dreamers, and builders to ask what if, and to pursue answers that lie beyond the known horizon. It equips us to have conversations about the future we want to create, a future with faster communication, better medicine, more sustainable energy, and a deeper understanding of the cosmos itself. The universe has handed us a new set of rules to play with, and it's up to us to see what kind of world we can build. So, the next time you look at the world around you, remember that what you see is governed by the laws of how light interacts with matter. And remember that we are now learning to rewrite those laws. We are just at the beginning of this grand adventure. The age of metamaterials is dawning, and it promises to be a time of wonders. The future is not just something that happens to us, it is something we can design, engineer, and build. And with tools like metamaterials, that future looks brighter and more extraordinary than ever before. The cosmos awaits.